Alright, I figured it'd be easier and you'd understand better if I just showed you a low pass filter. It's real common and I think it's better than the peak detection circuit. So here's how it works. Basically, a low pass filter is just a resistor and a capacitor. So if we watch the output of this, now I've already chosen the values that seem to work best with what you're working it with. It won't allow me to do, well, it won't, the simulator won't allow me to easily make a sine wave that doesn't go below 0 volts. It wants to go in the negative, so I have to use this, which is a 5 volt square wave pulse, 0 to 5 volts at 60 hertz with a 50% on and 50% off. So it'd be electrically, it's going to be similar enough to show exactly what you're doing. So let's see what this does. So we got the input right here. So green is what's being input, 5 volts at 60 hertz square wave. So let's remove that. So right now you're seeing it knock it down from 0 to 5 volts to 2.4 volts to 2.6 volt triangle wave here. So it's not very clean. That's really noisy, and anytime you want to read off of something like this, it's always best to use an op amp. Op amps come with 2 channels usually, and you just make a buffer. And to make a buffer, you just connect the negative to the output and the input to the positive, and that's a buffer. So if you were to put a load on the output, it would have no effect on this input. So you're getting an accurate reading here of what's there regardless of what load you put on. So that's why you use a buffer, So we're buffering. It's going to be the exact same as before, because this right here is going to be the same as this right here. So that's still that dirty triangle wave there. So we're going to do a second stage of the same thing, just 2 stages. I mean, there's 2 channels in an op amp anyways, you might as well. So here's another resistor, here's another capacitor. We're going to connect those up like this, and the capacitor to the ground, and I'm using the exact same values, and I'll show you why here in a minute. But I chose those values by playing with this in the simulator to find what worked best, and because this is a pretty low frequency, 60 hertz. So now we're going to turn this channel into a buffer also. So right here you would read with your analog read the output. So if we start it, you can see the blue is the first stage and the green is the second stage. There's a nice big difference there, So if we look at this blue, let it all settle out here. So the blue's still going, or first stage is still going from 2.4 volts to 2.6 volts in a triangle wave. So if we stop looking at the first stage and only look at the second stage, see, that's 2.5 to 2.5. It's whatever this triangle wave is, it's less than 100 millivolts triangle wave. So that's clean enough to get a good ADC reading. And the simulator doesn't show me a more accurate number, but it's pretty good. It's good enough. 2 stages is usually good enough for most things. And 10 microfarads for the capacitors and 10K for the resistors, I found to be a nice spot. I mean, you could go, say, I'm not sure what values are usually available, but I mean, you can go maybe a 47U and get an even cleaner frequency, but the response time is going to be slower. The bigger capacitors you use, and even the bigger resistors you use, you'll get a cleaner signal, but the response time to change is going to be a whole lot more, you know. So if the current you're monitoring changes, this system will take time to catch up to the change to give an accurate reading, to settle out, you know. So that's why we usually use stuff that's a little more reasonable, you know, like a 10U, and the 10K is reasonable for this 60 hertz. You know, 60 hertz is pretty slow. So, but that'll be perfect. This would be perfect for what you're doing. It's the exact same electrically, besides it's square wave instead of sine wave, but it should be the same. It's you know, now if you were doing the PWM output of the Arduino, and you wanted to smooth that out into a voltage, and also notice that this is a 5 volts and we're getting 2.5 on the output. See, and we can change that. Now this would represent the changing value for your device. It's going to be half the amount on the output, and that's because it's a wave that's half on and half off. So it's half on and half off, so it's going to be half the total amount. So if it's 5 volts, it's going to show up as 2.5 volts, and you know, whatever it is twice as much for the sine wave is. So yeah, you're going to get half as much out on the output. Just remember that. See, that's 1.57, and what do we turn it down to? 3.14. 1.57 times 2, 3.14. So it's at half the input, and it's a clean enough wave here that it's basically DC. It's clean enough for your analog read for sure. Now if you were doing, say this wasn't a 60 hertz pulse, say this was the PWM out of your Arduino, then that'd be a higher frequency. It'd be almost 1,000 hertz or better, depending on what settings you use. Then you'd use a smaller capacitor, and we only got this big, well, not really big, but this 10 microfarad because it's a slow 60 hertz. Now if you're doing a PWM signal out of an Arduino, you'd use like a 0.1 microfarad or a 0.01 microfarad, and then I usually use a 15K resistor for the resistor doing that. And then you can use a setup just like this to turn a PWM signal into a controllable analog output voltage. So it's a digital to analog converter if you run your PWM through one of these circuits. So this is how the low pass filter circuit works. So I hope this video shows how it works better than anybody else could explain it. So alright, later.